Institute there. Pioneer in algorithms and game theory and microeconomics. Has a whole string of awards, a Murray Grace Hopper Award, Kalai Prize, Gödel Prize, invited ICM speaker, Guggenheim Fellow. Very pleased to have Tim here telling us about a case study in blockchains and Web3. Welcome, Tim.
Just to echo some of the things other speakers have said today, it's a real privilege participating in the 10th anniversary for the Simons Institute. Happy birthday, Simons Institute. It's really, added a completely new dimension, I think, to being a theoretical computer scientist. I was lucky enough to be, sort of within spitting distance of the Institute for a number of the last 10 years. It certainly had a huge influence on my life. I've really enjoyed sort of engaging with it. And I just want to, for the students in the audience, just so, for some perspective, like if you ever have the feeling, you're reading some paper from like 20 years ago, and you're like, oh my God, I can't believe how easy the theorems were 20 years ago. I was born too late. I missed the golden age. I'm here to tell you, there's a lot of older people in this room that feel like we were born too early and didn't get to enjoy the Simons Institute until fairly late in our career. And so we are in one of the golden ages of theoretical computer science, and the Simons Institute is a big reason for why. Okay. I want to talk a little bit about blockchains and the applications that are being built on top of them, which is sometimes collectively referred to as Web3. Goals are pretty modest. I really just want to convince you that there's some super interesting computer science that goes into this technology. I'm biased as a theoretician, but I believe whenever you see super interesting computer science, you can usually bet that theory is playing a very fundamental role, and that's absolutely true in this application domain. If you know how to look for its fingerprints, you see it everywhere. Okay, and so I want to give you a glimpse of that today. Okay. But first, so I have to say, like in my 25-year career as a computer scientist, never have I seen a technology so widely and deeply misunderstood as blockchains and their applications. I think in part it's sort of a testament to the power of first impressions. So Bitcoin rolled out around 2008, 2009. And a lot of viewpoints, a lot of sort of narratives got very hardened very quickly in those early days. And while I think some of those viewpoints were maybe kind of at least semi-valid, 8 to 10 years ago, since then there's been many new generations of blockchain protocols. Our thinking, the evolution in our thinking of what they can accomplish has changed a lot. And so really what I want to do is just take an honest look at this technology in 2022, and not through the lens of investment or money or politics, but really just through the lens of computer science and specifically theoretical computer science. So in that spirit, let me just give you one slide. This is how I recommend, this is what I would suggest as a mental model for how to think about a blockchain. And I'm really thinking about blockchains here almost informally, but almost like a computational model. Like what computing functionality does this give us that we didn't already have before? And now just a couple caveats, like what I read on the slide, I'm not gonna claim it's literally true or even really like well-defined in a mathematical sense. But I do claim it's sort of a good mental model for thinking about what this technology might be good for and the technical challenges that will come up when you try to build it, okay? So what's a blockchain really? And so here I'm talking about general purpose smart contract platforms. So if something like Ethereum would be the biggest and best known example. There's many generations since then as well. It's a computer, okay? The way that your laptop is a computer. Okay, not like a physical computer, the way your laptop is, but rather the product of sort of a simulation of a virtual machine, okay, carried out by lots of nodes scattered across the internet. I like to think of it as like just kind of a big computer that lives in the sky, operating in public view, running basically as a public good. All right, so what? You all have computers on your wrists and in your pocket. Plus, viewed as a computer, blockchains are about as powerful as computers were literally like 50 years ago. So there better be more to the story. And there is. So it's a very unusual computer in that, in effect, it has no owner or operator. We'll talk exactly what this means in the second technical section. But you should think of it that there's no one who really has control over this computer. It runs on its own. For example, no one's in a position to shut it down. It's open access in the sense that anybody can use it. There might be, a usage fee, especially if there's congestion, but you don't need to be on any whitelist. You don't need to register anywhere. You can just use this computer. By use, I mean either sort of interact with existing software, meaning smart contracts, or install new software if you prefer. And finally, and maybe most interestingly, is the paradox that despite the fact that this computer in the sky effectively has no owner, it nonetheless enables a notion of ownership for its users. Okay, so if you're an end user of a blockchain like, say, Ethereum, you can own data that lives on that computer in a meaningful sense. And that computer in the sky will enforce property rights for digital data on your behalf. And I use the phrase property rights in the totally traditional sense of the term, okay, the way we're familiar with physical possessions, right? Right to use, right to transfer, right to exclude, et cetera. Okay, so this paradox, seemingly, of having an ownerless computer that through cryptography enables verifiable ownership, meaningful ownership for data stored on it, that is really the fundamental problem that Nakamoto figured out with the Bitcoin protocol, in my opinion. Nakamoto had in mind the very specific use case where what the digital data represented was a currency, was Bitcoins, but that is not fundamental to the technology. Okay, it's really just enforcing property rights for digital data. Okay. So I don't know how you would get this combination of properties before the advent of blockchain technologies, which makes it a logical possibility, certainly not a foregone conclusion, but a logical possibility that this new computing functionality might enable sort of truly game-changing applications, applications that change the life of a randomly sampled person on the planet, the way I think most of us would agree that the internet has at this point. Okay, and for that to happen, the application layer has to figure out exactly how to use this unique combination of properties that this computational model gives us. Okay, something on everybody's mind, just like, okay, so like, but what are those applications going to be? You know, like what's going to be the truly sort of killer app of having a sort of enforceable ownership for digital data? And it's not that there aren't any answers to that question. There are, but I think it's a little, it's been 13 years since the Bitcoin protocol rolled out, since we had blockchains. 13 years after the internet rolled out, that was 1983. If you'd asked anybody what were the killer applications of the internet in 1983, you would have gotten answers that did not resemble whatsoever what we think about today. It's not to say there weren't any answers. You could send email, you could transfer files, but it's just the really game-changing applications were still years in the future. And I would predict that the same kind of pattern is going to recur with blockchains and Web3. Okay, so on to the technical part of the talk, which I've optimized for breadth over depth. So I want to talk about 3 different topics, and I've deliberately chosen them so that they illustrate how totally different parts of theoretical computer science show up in this application domain. We're going to talk about algorithmic mechanism design, we're going to talk about distributed computing, and we're going to talk about proof systems. Obviously, I won't have time to talk much about any of these, but I hope it gives you a glimpse of all the different ways that theory is kind of playing an important role in this application domain. All right, so I want to start with this idea that the computer in the sky is open access, that anybody can use it. And so the question is, how do we make that actually economically viable? So, because here's the thing, right? I said that the computer in the sky is about as powerful as computers from the 1970s, right? So as you probably know, blockchains fundamentally, they maintain an ordered sequence of transactions. You can think of that as a payment if you like, or I encourage you to think of it actually as sort of a line of a program being executed in some virtual machine. But in any case, a blockchain maintains a sequence of instructions, and those are added to the blockchain in batches known as blocks. And those blocks only come along every so often, and they're only so big. Using Ethereum as an example, you expect to see one new batch of transactions every 13 seconds or so. A typical batch might have something like 200 transactions in it. So we're talking about something like processing 15 transactions per second, which maybe sounds like not that much, and it's not that much. That's what I meant by saying it was like a 1970 style computer. So what that means is that if you have a blockchain that's really quite popular the way Ethereum is, it means demand for the scarce resource of that blockchain's virtual machine, computation on that blockchain, that's going to be a scarce resource. Okay? Demand will be much, much bigger than supply. So no matter how altruistic you are, just the blockchain is going to have to figure out which transactions to actually execute in its virtual machine and which ones to exclude. There's no choice but to make that decision. So the transaction fee mechanism is the part of a blockchain that makes that decision. If you want to take seriously the idea this computer is a public good, we should be allocating that scarce resource in the most valuable way possible, that is to the transactions that would benefit most from inclusion. So that's the job of this mechanism, to figure out which are the transactions that are the most valuable. So let me tell you how this works in Bitcoin and how it worked in Ethereum until about 9 months ago, something called a first price auction. And it's supernatural. You can't expect the blockchain to know which transactions are the valuable ones. So you ask users to submit to basically tell you how valuable their transactions are to them. Now, you need to make them put their money where their mouth is. So they actually have to attach a bid to a transaction, which is then going to be paid should that transaction ever be included on the blockchain into one of these blocks, okay? Now, you might have a question like, okay, but to whom? Like, I thought this computer had no owner or operator. So who exactly is the user paying for it to have their transaction executed? Well, to answer that, let me unpack a little bit more about how these things work, okay? So, we talked about, so what does it mean to be ownerless? So really what I mean by ownerless is that there's thousands, hopefully, of different physical machines sort of collaborating through a consensus protocol to have a virtual simulation of a virtual machine. So they're responsible for coordinating with each other to keep track of this running log of transactions. I also said how new batches of transactions are added to that log, one at a time. And so how does that happen? Well, while all of the nodes collectively maintain the past, one node gets to unilaterally decide the next block of the future. Okay, so each batch of transactions is going to be added by one single node, not a cooperation for all of them. There will be a unilateral dictator for each batch of transactions. That'll be very important for us for our mechanism design problem. Okay, so now it's clear who the bid should be transferred to, right? So if your transaction winds up being included on this blockchain, if it gets executed in the virtual machine, there is one specific node who is responsible for it getting included. So that's the natural recipient of your bid, okay? So that's the first price auction. You have end users submitting transactions. They want to be executed by the blockchain. If executed, they pay the bid. Where does the bid go? To whichever block producer included that transaction in the batch that they added, okay? Now, if you know a little auction theory, little mechanism design, the first price auctions are pretty natural, but they also have some issues. And in particular, it can be very hard to reason about how to bid in first price auctions. We've known this for 50 years. Okay, being in the blockchain setting doesn't make it any easier, because basically you want to get away with like the smallest bid possible, but subject to actually being included. And the smallest bid you can get away with sort of depends on what your competitors are bidding. So you have to then sort of reason about your competitors' bids. Okay, and that's sort of a burdensome computation to require auction participants to do. If you've ever heard of something like a second price auction or the VCG mechanism, those are completely different. There, all you have to do is figure out your maximum willingness to pay. You report that to the mechanism, and you're guaranteed that's going to be your optimal strategy. So way, way easier to participate in second price type auctions than first price type ones. And so an obvious question, we could take this seriously as a mechanism design problem and ask, is there a better transaction fee mechanism than the one that has been in use? For example, could there be a truthful mechanism in the spirit of the VCG mechanism? Okay, so that's the subject of this first technical part. And one of the things actually that's very fun about talking about this topic, so first of all, one really neat thing that's going to happen is that blockchains are going to produce they're going to have some unusual idiosyncrasies, which will force us to take what would seem to be a well-solved mechanism design problem and really reconsider it from first principles. That's the first thing that's going to happen. The second really fun thing is that because this technology is so early, this is an application of mechanism design at a really unusually low layer of the stack, right? Like if you think about the internet, right? Lots of opportunities for people who do mechanism design at the application layer, right? Designing, I don't know, some two-sided, platform, for example, on the application layer of the internet. This is more like doing mechanism design for like BGP routing or TCP congestion control. This is really in the plumbing of blockchain technologies. Obviously, there's more applications for mechanism design sort of on top, on the application layer, but this is really down in the guts. Okay, and so this is something we never saw with the internet. We never saw mechanism design thinking really influence the key internet protocols, but we are seeing it influence sort of fundamental blockchain technologies. So I hope this seems like a reasonably natural question to you, right? So blockchains have to figure out what gets in, what stays out. We need the mechanism to do that. Why not seek out the best mechanism in some sense? At the time that I did this work, which was sort of late 2020, it was also a super timely question specifically for the Ethereum blockchain, because at that time they were contemplating making a big change to their transaction fee mechanism. I'll tell you about that change in a second. So it was a mechanism proposed in the Ethereum Improvement Proposal, EIP, numbered 1559, and it was very controversial. We can talk in the Q&A why it was controversial if you like, but it was controversial. Some people really liked it. Some people either hated it or at best didn't understand it. So this is a survey that was run by Tim Byko. Again, this was late 2020. So he reached out. He's a key member in the Ethereum community. He reached out to lots of stakeholders, people who sort of design software wallets, people who are block producers, people who runs exchanges, and asked everybody, do you think we should switch our transaction fee mechanism to this new one, okay, to this new, more complicated one? And if not, why not? And is there anything we could do to make you more comfortable with the prospect of sort of this change? And people raise various things, but what I want to highlight here is, quote, the lack of a formal specification or proof for the mechanism for people to independently evaluate and critique. And I want to emphasize, not a single respondent to this survey was someone who writes academic research papers. These are all people who build things in the Ethereum trenches. And yet there was a visceral hunger from this community for what we do, okay, for theoretical computer science. That was like the missing piece for getting sort of sufficient support about this big change to the Ethereum blockchain, okay? So there's no question that was a big motivation for why I went and did this work. Oh, sweet, there's water. So what's idiosyncratic about the blockchain setting? Why do we have to rethink mechanism design problems from first principles? We have the usual issue, you have an auction design that you have to worry about people misrepresenting their preferences, like bidding, sort of artificially trying to shade their bid in a first price auction. We have standard language for saying we would like mechanisms robust to this kind of sort of gaming. It's a truthful mechanism or a DSIC mechanism, okay? This is the usual challenge, that's why I've labeled it challenge 0. Challenge 1 through 3 are really specific to the blockchain setup. So first of all, I made a big deal in emphasizing that when a new batch of transactions gets added to the blockchain, there is one node that is selected to have unilateral control over the contents of that block, okay? And so what that means is when you're designing a mechanism, right, you can, from your armchair, write down a design that you would really like these nodes to carry out, but ultimately they can do whatever they want, okay? The node selected at random to produce the next batch can run, in some sense, whatever transaction fee mechanism it pleases, okay? So the second incentive compatibility guarantee we're going to need, which again, this one is new, is that we're also in a mechanism that should not just be robust to the participants in the auction, but also to the party tasked with carrying out the auction. So the auctioneer or whoever is carrying out the mechanism is not a trusted party. It's a profit maximizing block producer, and our mechanism should respect that fact. So MMIC is going to state that it should be in the block producer's best interest, if it wants to just maximize its own revenue, should be in its own best interest to actually carry forth the transaction fee mechanism that you're proposing, okay? Also, the block producer, in addition to sort of excluding or including whatever it wants, it can basically costlessly inject its own fake transactions. And the reason you never hear about a second price auction of the VCG mechanism in a blockchain setting is this, okay? It's because second price auctions are really easy to manipulate if you get to sort of see all of the bids and then after the fact inject a shill bid of your own. It basically devolves into a first price auction, okay? So our first new incentive compatibility constraint says block producers should be motivated to carry out the mechanism you write down. And then the last thing I want to highlight is something I call OCA proofness. OCA here is for off-chain agreements. So we've already talked about robustness to manipulations by users and by block producers. This third one is about manipulations by cartels of block producers with users. Okay, this is very easy to carry out in a blockchain context through, for example, smart contract functionality. You also don't have the legal channels familiar from the real world that one often uses to sort of deal with collusion. So here, you usually punt on collusion in sort of traditional applications of mechanism design. You cannot afford to do that in a blockchain setting. You need to design a mechanism that really the mechanism itself makes it unprofitable for cartels to manipulate your mechanism. So the technical question then is going to be, we have 3 incentive compatibility guarantees on the slide, right, corresponding to robustness to manipulations by users or block producers or cartels of both. And the question is, does there or does there not exist a transaction fee mechanism that satisfies all 3 simultaneously, okay? So let me tell you about the mechanism that Ethereum wanted to switch to, okay? And then we can assess how well it does on those 3 incentive compatibility criteria that I just laid out, okay? 3 big ideas in this. First big idea is a reserve price, okay? Which is a standard thing you do in auction theory. Interestingly, if you use a reserve price in the most obvious way, okay, meaning transferring revenues generated by the reserve price onto the block producer, the person responsible for that block, actually the game theory goes haywire and you lose that OCA proofness property that I talked about. Reserve prices of that form can be evaded by cartels of users and block producers. As a consequence, this transaction fee mechanism does something quite non-standard, which is it takes all of the revenues, all of the payments of the reserve price and burns them. By burn them, I mean literally removes those coins from circulation forever, okay? So they're paid by the end users, they go to nobody, all right? That fixes the game theory, that's gonna restore the OCA proofness property. Second big idea is to figure out, okay, so what should this reserve price be? Okay, and a natural idea is to use local search. If the price looks too low, raise it up a little bit. If the price looks too high, bring it down a little bit. How do you know, okay, from what's happened in the past, whether your current price is too high or too low? And so here the idea is to use variable size blocks. Historically, Ethereum had a hard cap on block size, like 200 transactions per block. And with this change, they said, you know what, let's just make that kind of a soft constraint. Let's have a target of 200 transactions per block, but allow it to be more or less. Okay? You still need some kind of hard cap for technical reasons. So let's say you could go up to 400 transactions if you want, but we're really targeting 200 transactions per block. Now you have just publicly available information which tells you exactly how to run your local search algorithm. If the last block was too big, that means your price is too low, you should raise it. If the last block was too small, like only 150 transactions, that suggests your current reserve price is too high, not enough people are willing to pay it, so you should decrease it. Okay, so you use the pattern of blocks and whether they're above or below your target to do the adjustment process on the reserve price. The third, maybe least important property for our purposes is sort of an emergency backup first price auction, which is part of the mechanism. So users have the option to paying above and beyond the reserve price if they want, something known as a tip, and then that tip gets transferred to the producer of the block, just like bids did historically in first price auctions. Okay, so that's the new transaction fee mechanism that was being contemplated, basically congestion pricing using block sizes to figure out how to adjust the reserve price, with the reserve price necessarily being burned for the game theory to work. Okay, so we've got our 3 incentive compatibility guarantees, so we can formally assess this proposed mechanism. How well does it do? And I don't know that I'd give it an A+, but I would definitely give it an A. Okay, it scores. It's a Pareto improvement over first price auctions. First price auctions satisfy the MMIC and OCA proofness guarantees. Pretty easy to see. As we discussed, they're really not truthful at all. This new transaction fee mechanism satisfies those same 2 properties, the 2 new incentive compatibility guarantees, and is also in some sense usually truthful. Okay, it usually acts like a posted price mechanism, which is a truthful mechanism, except in one particular edge case. Okay. The edge case being when you've just had a very long period of low stable demand, and you have a sudden demand spike, meaning that you would like to sort of instantly have a much higher reserve price. But the mechanism is going to sort of gradually increase the reserve price. So there'll be this period of like a few minutes where it acts more, it sort of reverts gracefully back to a first price auction. Okay, so the theorem says that's the only edge case. There's this obvious scenario in which truthfulness fails. Unless you're in the obvious scenario, actually you have the DSIC guarantee that you wanted. I also proposed a sort of an alternative mechanism, which moves that usually in front of the second guarantee. So always MMIC, always truthful, usually OCA proof with the exact same edge case. And actually, there's a really nice paper out of Carnegie Mellon, Hao Chung and Elaine Shi, who show that actually you need that usually. Okay, there's actually an impossibility theorem now saying you cannot get all 3 of these incentive compatibility guarantees simultaneously. Okay, so you need to make the small compromises either in EIP 1559 or in the tipless variant. Okay, and then I guess just to finish that story, 9 months ago, Ethereum did in fact switch to using EIP 1559, and it's been humming along ever since. All right, so next technical part, I want to remember the computer in the sky. I said it was ownerless, right? So what do I mean? Right, so I mean there's thousands of physical machines running a consensus protocol, keeping in sync about the current state of the virtual machine, okay, that blockchain represents. Right, so we should talk about consensus. Totally classic topic in theoretical computer science, right? A couple Turing Awards have been giving out to Lamport and Liskov. Fundamental work in the 1980s, 1990s, and since then as well. Which, right, it's kind of amazing, right? So obviously in the 1980s, researchers working on consensus were not thinking about blockchains. Blockchains were not a gleam in anyone's eye. And yet, as we see so often over and over again in theory, right, if you get the abstractions right, if you get the definitions right, okay, they're going to be exactly what you need 40 years later for some application you never could have anticipated. And there's yet another example of that phenomenon. Now, so they identified the consensus problem, but were working in what we would now call a permissioned consensus setting. What does that mean? That means when you fire up your consensus protocol, right, so you've got a bunch of physical machines all running copies of a piece of software. Permissioned means you know all of those machines up front. Okay. So for example, maybe IBM, wants to replicate a database, get really high uptime. So it buys 7 computers, puts them all over the world, so it can tolerate 2 failures and still stay in sync. Okay. Permissioned assumption, totally reasonable for those 1980s style applications. The vision for blockchains, the reason blockchains do consensus is different. Okay, it's not really for replication. It has the effect of replication, of sort of better uptime, but it's really for this ownerless property, right? That's really what you're after. And so accordingly, the vision's a bit different. Any of you right after this talk, you could go to your laptop, you could download software for the Bitcoin protocol, you could start running it. Your computer would literally be one of those physical nodes contributing to the consensus protocol that drives, for example, the Bitcoin protocol. Okay, so this is completely different than the permission setting. You have no idea, now or ever, who exactly is going to be running your consensus protocol. And so a priori, it's a great vision. A priori, from a theoretical perspective, it's not at all obvious there should exist any protocols that give you provable guarantees in the permissionless setting. Okay? And that really, from a technical perspective, you can view that as sort of the key theorem, if you like, in Bitcoin that Nakamoto came up with, figuring out how to do permissionless consensus so that you get the kinds of consistency and liveness guarantees that we've been accustomed to ever since the 1980s. Right? Now, my point on this slide is that not only is the permissionless consensus protocol design space non-empty, but it also has sort of multiple different looking inhabitants. Okay, so I want to talk a little bit about theory that we've been doing, trying to map out this design space of permissionless consensus protocols. So let me just concretely give you two examples of two protocols that look quite different from each other. First one, the original one, Bitcoin. I would say two big ideas, okay? So the first idea is, how are you going to select a node to get this unilateral sort of power to add the next block to the blockchain? Okay, so how do you figure out which node is the next block producer? To solve that problem, you need something known as a Sybil resistance mechanism, right? So you basically need to make sure that just, you can't have someone, generating a million sort of public keys for themselves and tricking you into selecting them almost all of the time. So you need some way to sort of, select a node at random with some probability that they cannot easily manipulate. The way that's done in Bitcoin is what's known as proof of work. We don't really need to know much about the details. If you've heard about hard crypto puzzles, that kind of stuff, that's this proof of work business. Point being, it's a Sybil-proof way of randomly selecting a node to decide on the next block. Okay, that's the fundamental point. The second thing you need is some kind of consensus protocol, right? Given the blocks that have been proposed to date, you need some sort of algorithm to tell you which of those blocks are actually finalized and in what order they should be executed. Okay, and so here also famously in Bitcoin, there's the longest chain protocol, which says, you may have forks, you may have different blocks with a common predecessor. Don't worry about it. The longest chain is the only one that matters. Okay, so that's the consensus rule in Bitcoin. Now we know very different looking permissionless consensus protocols. Let me highlight one I'm sure you're going to hear more about on Wednesday when Silvio speaks, which is Algorithmic. Okay, but there's a bunch of other protocols that have from 30,000 feet look fairly similar. Point being is just it makes. If you look at the two big design decisions in Bitcoin, Algorand does both of those steps differently. It has Sybil resistance random sampling, but it does it in a different way. It does it not based on proportional to computational power, but rather proportional to how much stake in a native currency you have locked up in a certain smart contract. Okay, that's the way they do Sybil resistance. And then consensus in Algorand and many other blockchain protocols actually is not longest chain consensus, but rather is really kind of, basically builds on, it sort of stands on the shoulders of the classic protocols from the 1980s and the 1990s, which I'm going to call BFT type consensus. Okay, and again, the details there aren't so important. I just want you to know that there's multiple permissionless consensus protocols and they look quite different. Okay. In addition to these two examples looking quite different operationally, they offer you quite, fairly different provable guarantees. Okay, and so the main thing I just want you to focus on here for these mathematical guarantees is that they're incomparable. Okay, so when you're analyzing a consensus protocol in a distributed system, you're kind of worried about adversaries of two different types. First of all, some of the nodes running the protocol may be either buggy at best, or even a malicious actor trying to mess up your protocol. So one kind of assumption you're going to need is you're going to need some lower bound on how many of the nodes are running your protocol correctly. Okay, that's the first kind of assumption you need. The second thing you're worried about is the communication network. Okay, and you're worried about the possibility of message delays and whether, and how severe those can be. All right. And so the point is Bitcoin's going to make a stronger assumption along one axis and a weaker assumption along the other axis. Okay, so specifically, the good news about Bitcoin is the bad news is that it makes very strong assumptions about the communication network. It assumes that there's an a priori known bound capital delta. Every message that anybody ever sends to anybody else is guaranteed to arrive within delta time units. Okay, so it's really an appropriate model for sort of normal operating conditions of a network. It's not appropriate when you have network outages or denial of service attacks. Okay, the good news about Bitcoin is it can tolerate, all it needs is a strict majority of the nodes running the protocol, or more formally, the computational power running the protocol, and needs a strict majority to be running it correctly. And then you actually get provable liveness, provable consistency. Consistency just means all the nodes stay in sync with each other. Liveness just means that as long as there's work to do, the nodes keep doing it. Okay. Algorand, meanwhile, one of its claims to fame is that it's robust even under network attacks. And so the formal definition is it operates in the partially synchronous model. Okay, so this is the sort of standard definition. So this is, from the 1980s, the standard model that's sort of a sweet spot between the synchronous and the asynchronous models, which in particular is a good model for denial of service attacks of unbounded duration. So that's the good news, weak assumptions about the communication network. The bad news, stronger assumptions about the fraction of the nodes that are running the protocol correctly. Okay, it used to need to be 51%, now it needs to be 67%. As usual, as theoreticians, right, you see multiple incomparable solutions. You have to ask, for example, can you get the best of both worlds? And if not, why not? More generally, like I said, I want to map out this permissionless consensus protocol design space, right? You have these different protocols, they look different. Do they need to look different? Are there different mathematical properties driven fundamentally by the different design decisions or by something else? So this is sort of a series of works I've been collaboration with Andy Lewis Pye, who's a professor at London School of Economics. And so the agenda of our work is to say, let's start from the mathematical properties you want your blockchain protocol to have. To what extent does that dictate design decisions you make along the way? Right? So does some mathematical property dictate that you have to do Sybil resistance using proof of work versus proof of stake, or consensus using longest chain versus BFT type, something like that? To what extent do the mathematical properties desired force you into certain design decisions? Okay. And so the punchline here is you can prove theorems along these lines. So for example, both of these are informal. I'll be a little bit more precise about the first one in a second. But basically, for example, for Algorand and its property that it gets consistency even under the presence of network attacks, even in the partially synchronous model, it's required, okay? It's a necessary condition that it uses proof of stake Sybil resistance or something like it. It's a necessary condition that it uses BFT type consensus or something like it. In other words, you could not have any kind of variation or tweak on Bitcoin or any other longest chain protocol or proof of work protocol that captured the same guarantees that Algorand has. It's really fundamentally driven by both of the two design decisions I told you. Okay. I know that's a little vague, so let me be just a little bit more precise on that first statement, and then I'll just very quickly talk a little bit about proof systems. So again, this is ongoing work with Andrew Lewis Pye. So, we came up with a general model. We had to be agnostic to how you were doing Sybil resistance, how you're doing consensus, all that kind of stuff. A lot of details, as you can imagine, but the part of the model I want to highlight is this idea of a resource pool. So we propose analyzing a blockchain protocol in conjunction with a resource pool, which specifies resource balances for all of the nodes. What's a resource balance? That's basically the amount of control over the protocol's operation that node has. For example, for a proof of work blockchain, your resource balance is going to be the amount of computational power that you bring to the protocol. In a proof of stake blockchain, your resource balance is going to be the amount of stake you have locked up in some smart contract on the chain. In general, abstractly, the resource balances just say how much power you have over that protocol. There's a very important distinction. Okay, we never actually define proof of work or proof of stake in our work. That's like a little too operational for our tastes. But we have a notion of the sized setting, which means that your resource balance, your control over the protocol, should just be publicly visible given the state of the blockchain, given everything that's happened in the past. And if you think about it, proof of stake is an example of a size setting, right? Because it's literally just how much stake you have locked up in a smart contract that lives on the blockchain. Anybody can look and know exactly everybody's resource balances. Unsized setting means actually they evolve independently, and their proof of work would be an example. Right, if a bunch of people turn off their machines, that's in no way reflected in the blockchain state. Okay, you have no idea. So unsized setting you should think of as a proxy for proof of work. So that first informal statement that I gave that really sort of proof of stake is essential for Algorand's guarantees, here's the formal statement in terms of an impossibility result. Basically, if you operate in the unsized setting, so if you're a proof of work blockchain, you really must choose between some very basic minimal liveness guarantee, which you sort of obviously want, and consistency in the partially synchronous setting. In particular, right, if you think of 2 as kind of a hard constraint, then 1 and 3, you have to pick one or the other. Bitcoin picks the first one. It does work in the proof of work setting, but it gives up on consistency in the partially synchronous setting. Algorand makes a different choice. It is proof of stake. It's not in the unsized setting, and it does get both liveness and consistency in the partially synchronous setting. So this is what I mean by proof of stake, or just generally having some sized approach to resource pools is absolutely fundamental to the guarantees you get from Algorand. Okay, so Bitcoin's reliance on proof of work forces its compromises when you have network attacks. Very briefly, third topic, I can't not say this given the audience. If you study a little bit of complexity theory, you study proof systems, right? And it's hard to understate how deeply embedded in the fabric of the sort of just culture of theoretical computer science is proof systems. And I'll defer to the people in the room who actually sort of invented this concept. But my understanding is that really proof systems were sort of developed, so by proof system, I mean you have a prover, you have a verifier, a conversation between them. My understanding is they were really invented to basically sort of understand the mysteries of the computational universe, right? Like, what is a proof, for example? Your first thought might be open up a math book, right? There's a proof. That's sort of the NP notion of a proof, right? So think instead about a teacher and a student having a conversation, and you want to know when does the student leave sort of having learned some property, right? And that's different. There's interaction, there's potentially randomness, and so that gave us a proof system. Okay, what really is a proof in sort of the broad sense of the term? As you all know, this definition led to many of the most famous theorems in our field, right? Zero knowledge for all of NP, the PCP theorem, IP equals P space, et cetera. Amazingly, with blockchains, there are now multi-billion-dollar startups, okay, including ones founded by this community, members of this community, where what they are doing is practical implementations of proof systems. Okay? I'd be curious if anyone anticipated this happening back in the mid-'80s. I'm guessing not, but I'm not totally sure, but that is happening. So again, 40 years ago, theorists captured something extremely fundamental. We all knew it was fundamental right away. It was sort of obvious once you learn it, I think. But it's fundamental not just in a purely intellectual sense, but it's actually exactly what you need for blockchains to reach their full capabilities. So I'm just going to say a tiny bit about that, just so you understand what I mean. It's about scaling. It's about making the computer in the sky more powerful. Okay, I told you it's very weak. Maybe 15 transactions per second. It's like it's from the 1970s. How do we at least get it up to like the 1990s or something like that? One approach is to graft in additional computation from outside the blockchain. Okay, typically this would be a third party, but even just imagine you've got Ethereum, and you've got someone who's like a really big fan of Ethereum, and they happen to have this like super powerful computer, and they're like, yeah, Ethereum, let me help you out a little bit. Let me take some of the load off of your shoulders. Okay, I'll do some transaction processing. I can do 10,000 transactions per second, no problem. And I'll just kind of give you periodic updates. I'll give you like an FYI. Hey, I processed all these transactions. Here's the state diff. Okay, so here's the new state of the virtual machine given the computation that I did. And why would you do that? Well, now, right, this should be a Pareto improvement over the current situation. Current situation is basically if you want to use Ethereum, you have to send it to this sort of to this computer where computation is very scarce and therefore very cheap. But here you're going to have a second option to send it to this off-chain computer where computation is abundant and therefore should be cheap. Now, if you think about it, for this to work, these periodic updates better be verifiable, okay, by the Ethereum blockchain, by the computer in the sky. Otherwise, this so-called fan of Ethereum might just say, hey, I did all these transactions. In the new state, it just so happens that I own all the coins, right? And that's not okay, right? So Ethereum needs to be able to verify, okay, that the resulting states that the off-chain computer allegedly computed actually is correct. Okay, so they need to be periodic verifiable updates. And there's a specific type of proof system, which again was studied way before blockchains, 15 years before blockchains at least, known as snarks, which is exactly the construct you need, exactly what is needed to make this idea work, okay? It's a specific type of proof system. Again, there's many people in this room that know much more about this than me, but let me just, for those of you that are wondering, what's the acronym about? So the S is for succinct. This is kind of, for this, off-chain computer to take any load off of Ethereum's shoulders, it better be the case that the amount of work Ethereum has to do to verify the proof of correctness is less than redoing all of the work from scratch. Okay, so that's basically what the role of the succinct plays. I talked about proof systems as being interactive, the teacher and the student. Permissionless blockchains, right? Nodes can just sort of go down, disappear forever. So you don't want to assume that the people who came up with a proof a long time ago are still available and online. So you really want non-interactive proofs. Okay? You just want a single proof that's posted once and for all to the blockchain. Everybody can read for the rest of time. Argument is just sort of basically proof. Basically, it should be verifiable. So you can correctly prove if you did do the computations correctly, and you can't prove if you didn't do them correctly. Knowledge, this is also important in the blockchain context, but actually not quite as important as the first three. Okay, so the first three are really totally essential for this grafting and off-chain computation idea to make sense. Okay, and so last slide, and then I'll wrap up. The final thing I want to say is, initially in the early days of proof systems, right, the focus, my understanding, is really on kind of, the structural complexity aspects, right? IP equals P space, sort of understanding the relationships between various classes. Once that's been sort of mapped out, it's natural to look at a more fine-grained approach, okay, to actually sort of study various resources you might want to minimize and ask exactly how many resources are necessary to prove various types of statements. Okay, and this work has been going on solid for my whole career, basically. And maybe no surprise, but it's still like just amazing for me to sort of see this. If you look at the metrics that theorists sort of focused on, just because they seem like the obvious natural ones to focus on, like verifier time, proof length, and approver time, those are literally exactly the metrics that need to be minimized for this whole snark thing to really take blockchains to the next level of power. Okay, so length of the proof, that's going to correspond. Oh, so the one, I hope it was clear, but as far as the analogy, the big computer in the sky, this is the verifier in the proof system sense, right? This is the party that has less knowledge and or less computation, and then the off-chain computer is the prover. That's the one with more computation and or more information. Okay. And so with that in mind, right, so the length of the proof, which is something we've always tried to minimize, that corresponds to footprint on this sort of big computer in the sky, where storage is scarce and therefore expensive. Similarly, verification time, that's computation done by the virtual machine, the Ethereum virtual machine, the computer in the sky, which is also very expensive. Prover time, this is what people are now working really hard to sort of minimize as much as possible, because this is really what's going to limit sort of exactly how many transactions that off-chain computer can offload from Ethereum, right? If it takes, n to the 10 time to generate the proof, it's not going to be able to generate a proof for that many transactions. Okay, so getting this prover time small, we'll see, like it's getting better and better and better. And ultimately, if it gets small enough, this literally will be the roadmap that wins for the scaling of blockchains. Okay. So let me wrap up here. Just the main point, think of a blockchain. It's a general purpose computer in the sky. It's open access. Anyone can use it. It's ownerless or operatorless in effect, meaning it's run by this consensus protocol across many different nodes. It enables the enforcement of property rights for digital data that lives on that computer. And there's lots and lots of interesting computer science, and specifically theoretical computer science, that's absolutely essential for it to realize its full potential. Let me stop there. Thanks.
All right, thanks very much, Tim. Just about the impossibility result. Is it clear that there's always something negative about the what you called the unsized setting? Is it, for instance, required that there's an energy consumption cost associated with that?
Okay, good question. Yeah, so that's a related question. So again, in our model, we don't define proof of work per se. We just define unsized, which basically means you can't automatically deduce the resource balances from the on-chain information. If you want to talk specifically about proof of work, energy consumption may well be fundamental to the proof of work approach to civil resistance. There's no real, I mean, people have tried to have versions of proof of work that are less energy consumptive, but really the road forward there simply looks like proof of stake blockchains and other alternative civil resistance mechanisms. Yeah.
Yeah, thanks. I learned a lot about, of course, I see all this stuff in the news. I don't really know how it works. I learned a lot today. One thing that I guess really caught my attention is you mentioned Bitcoin makes this assumption that, more than 50% of the CPU power running the protocol is honest. And I'm curious, I think the value of all Bitcoin in the world combined is less than $1 trillion, which is like not that, it's a lot for me, but it's, much less than the budget of the US government, for example, or put together a few Senate billionaires. is there, I mean, is that a risk that, Bitcoin could be over if some government decides one day to just like take over I mean, does one government have enough power, for example, or like budget to just take over Bitcoin?
Right. So it's a good question. So it's a question about basically 51% attacks. So really, so it's kind of a question of like, how real is this? When I say it sort of has no owner or operator with much control over it, to what extent is that actually true? Right. So which is an important question. And like an extreme failure mode would be if a single actor took sort of single-handed unilateral control of the blockchain. For example, for Bitcoin by acquiring 51% of its hash rate. So the first question is just like, so a couple of things. I mean, so certainly when you're designing blockchain protocols, you want to think about those issues and you want to think about ways to make attacks on it as expensive as possible. Separately, you also want to think about kind of, recovery plans in the event of a 51% attack. Right, it's sort of funny, right? Because like, if someone took over Bitcoin and started sort of, forked it and had all these new blocks, I mean, everybody would be, it would be in plain view. Everyone would sort of know that happened, right? Now, if you just go the code as law route and literally just follow the protocol, then in some sense, there's nothing anybody can do, right? This is the new longest chain. There's nothing you can do about it. But in reality, right, these protocols kind of exist in this broader social context, right? And if there is some reason for everybody who is sort of running the old Bitcoin nodes to kind of say like, oh no, let's just sort of upgrade the protocol, have a different version, like we'll call the new version like Bitcoin Prime or something, then it's just about convincing vendors that they should pay attention to the record on Bitcoin Prime rather than on the original Bitcoin, which had been taken over. So it's hard to see how to do theory about that, but the point is, it's sort of like failures at the consensus layer kind of escalate up to the social layer, where if you have sort of enough norms around what to do in the face of an attack, it's certainly not obviously an existential threat, put it that way. It would be very disruptive, right, for someone to take it over and needing to kind of fork off a different version, but it is something one could do. So.
Hi, first of all, thank you very much for this talk. I had a question, but then I came up with an answer. I'll ask it anyway. Maybe you'll have a different answer. How important is the N in snarks? I mean, if you want to have this off-chain CPU that runs this offload, takes this off the shoulders of the chain. So how important is it that it would be non-interactive? Maybe you can do better things if you let it do interactive stuff.
No, it's a great question. The question was about how essential is non-interactivity really? I would say for the original, like Bitcoin, Ethereum vision, it's pretty important. Where you really just had in mind 50 years later, someone could sort of download some software, read the last 50 years of the blockchain, and then just sort of catch up and sort of go from there. Because again, who are you going to interact with for some proof that was posted 40 years ago? But there's no question, especially, and this is now maybe more at the application layer than at the consensus layer, but definitely there are situations, these I don't know that any of this is in production. There's certainly groups experimenting with this idea of doing a modest amount of interaction. So basically making more assumptions about how long people are online in order to accomplish sort of something better. So absolutely. I mean, I don't know, like I said, I don't know that interaction is going to be ever a thing at the consensus layer that we talked about, but in the space broadly, it's definitely important. Yeah.
How much everything trivializes if you were willing to live in the permissioned consensus world? So suppose you wanted to generate a blockchain, but where you have 10 parties where you maybe trust all for liveness, but majority for safety, for correctness or something like that. And there are known parties, some non-government, whatever. Is everything trivial and everything solved in that setting, or is it still interesting?
Well, it depends what you mean by everything. I mean, what the main thing you do is the 51% attack issue goes away, I would say. You just no longer worry about that, right? So at best, you trivialize what's happening at the consensus layer, right? But there's this big stack of things going on, right? So there's still the stuff about like, how do you scale up the basic consensus layer, but it doesn't help you with that. Well, it might help you, but it doesn't trivialize that problem. There's also just all of the questions at the application layer. It really doesn't trivialize any of those problems either. I mean, the main thing, the main sort of trade-off that people are playing with, I'm very curious to see how this plays out. It's one of the things that's actually super fun about the space is even though I've now kind of thought a lot about a lot of aspects, there's so many things that I have no idea how they're going to play out over the next 5 years. It's just really interesting. And so Right. So one of the reasons you only get the 15 transactions per second is because you have tons of nodes. It's very globally distributed. And so the main thing, if you sort of have fewer nodes, independent of whether or not you sort of know who they are, but if you just have like a more tightly coupled network of 30 nodes, you can just do way more processing because there's just way less coordination required. So if these things really go mainstream, will it be with kind of a scaled up version of Ethereum like I discussed? Or will it be with more like an architecture that uses kind of a small, tightly knit set of maybe, partially permission nodes or something like that? And definitely there are groups exploring all these different parts of the trade-offs, and we're just gonna have to see what happens, so.
All right, we'll stop it there. Join me in thanking Tim again for a fantastic talk.
Okay. Thanks.